Hi folks, it's Mr. Moodledge here with another video. This time we're looking at lesson number 6, which is talking about transformations in the horizontal direction. So we're looking at horizontal stretches and compressions in this case. So where we begin is just by looking at the parent function, so square root of x, and looking at what happens when we modify the input here inside the square root. So for instance, we have 2 times x inside here, and we would have 1/2 times x. Here the 2, so our k value is 2, so we would say this is a horizontal compression by a factor of 1/2, right? Because with k, it operates the opposite way to how, like, for example, a would work. So we have to say by a factor of 1 over k, and in this case k is 2, so 1 over 2 is the factor there. Here it's the flipped version of that, so we have a k value of 1/2, so 1 over 1/2 is the same thing as 2, so we say this is a horizontal stretch by a factor of 2. So what this looks like is, if we're going to graph this, the black line right here, that is my parent function. How do I know that? Well, square root of 0 is just 0. Square root of 1 is 1. Please note the scale here goes up by units of 1, and in the y-axis it goes up in units of 1/2. But yes, square root of 1 is 1. Square root of 4 is 2, and square root of 3 is 9. Square root of 16 is 4, and you get the idea, so on and so forth, right? That's for an input of 16 here. So that's the parent function. Good. Now if we take a look here at y equals square root of 2x, well, I'm only modifying my graph. I'm transforming it horizontally. I'm not actually stretching it vertically or moving it up. Well, I'm not actually, sorry, I should rephrase that. I'm not actually translating it vertically or horizontally. So there's only horizontal transformations going on here. Specifically, what's interesting about this is if you take a look at what value of x would give me the same output as, like, for example, if I wanted the answer, like, I know when x was 1 here, I got an output of 1, right? If I wanted an output of 1, what would I have to make x here? Well, it turns out I would want the inside of the square root to be 1, and that's only the case when x is 1/2. So you can see how for the same y value, like for the same y value of 1, for the instance where it's horizontal compression by a factor of 1/2, so this one right here, well, x would have to give me, x would have to be 1/2 for me to get the same y value of 1. So essentially it's being compressed vertically, horizontally by 1/2, right? In the other case right here, x would have to give me 2. So an x equals 2 would have an output of y equals 1, right? So it got stretched horizontally, right? Take a look at the next x value. That's nice. At 0, they're all 0, so they all coincide, right? 0, 0, 0. That's okay. Essentially, what value of x would give me the square root of 0? So it's just 0, so that's why they're the same. Next, the nice next parent function, like square root in here, would be square root of 4. So that would be right here, right? So in order for me to get 4 here, the answer would be 2, square root of 4. In order for me to get an answer of 2, I would want the square root here to be 4. That's only a case when x is 2. So notice when x is 2, I get a y value of 2 for this function. And for this one, well, it's the opposite, right? If I wanted an answer of 4 here inside the square root, my input, I would want, well, inside the square root, I would want x to be 8. So essentially it got doubled, right, from here to here for the same y value. So that's kind of how you can graph these. It's a good way to picture that, why it's the opposite, why we say it by a factor of 2 multiplied, when even though it's 1/2 there, it's because we're looking at what value would make the square root retain the same answer as the original y. So we could see that, when we're talking about the same y, well, we're compressing, we're stretching it this way, and we're compressing it this way, right? It's compared to the parent function. Okay. We have some examples like this. So let's say the black line, which is drawn here. So yes, the black line is like the function that we have in question. And there are many ways to go about this, but if we're just looking at points, well, we're just going to pick a point, or sorry, we're going to pick a point right here in the black function, so that on the black line. So right here, that has a, an x value of -5. And if we're looking at this right here, so this is a horizontal stretch by a factor of 2. So we're going to double it, right? -5 times 2 is -10 for the same y value. This point right here is going to get doubled, right? So -3 becomes -6. This point, the x value is going to get doubled. The same y value, but the x is going to get doubled, right? So it gets to there. Likewise, this point is going to get doubled 3, the x value, to get to 6. And this point is going to get doubled, the 6 to get to 12, and so on and so forth. And you can see we get, when you connect the points, we get this pink line right here. It's the opposite in the case of this, where it's a horizontal compression by a third. So we would divide each of the x coordinates, in this case, -5 by third, we multiply by third or divide by 3, same thing, to get that x value right there. Here, -3 divided by 3 would give -1, right? -3 times a third would give -1, and so on and so forth. You could see that it's gotten compressed by a factor of a third. Okay, so that's how that works. Moving on here, we could see that, so we have our parent function. I want to sketch the transformed function, which I give the name g of x. So I'm just looking here at these different, transformations. The negative is a reflection about the x-axis. It's like a vertical reflection, up, down, right? The half right here for k is a horizontal stretch by a factor of 2. The +6 here, it's 6 units left, right? So d value. The 7 right here is I move it 7 units up. So that's how that works. And then I could see here, well, this is what my parent function looks like, square root of x. And then I'm just going to apply the mapping rule here. So, if I pick a point here, I'm going to reflect that point. If I wanted to do this intuitively, right, I'm going to reflect that point. So that's dealing with the vertical reflection right there. And then I'm going to move it 7 units up. So 1, 2, 3, 4, 5, 6, 7. So it's vertically, that's where that point's going to lie. The next thing I'm going to do is horizontally compress that point right there. So I was right here, by the way. So horizontally compress that point, horizontally stretch that point by 2. But since it's 0 horizontally, like the x value is 0, it's just going to stay at 0. And then I move 6 units to the left. So 1, 2, 3, 4, 5, 6. So that's how I could do that very quickly. These are the mapping points right there, the mapping rule. I could do that to get this function right here. So that works out. If I picked this point right here, 4, 2, let's try that. So first thing, I want to reflect it vertically. So 4, 2 would become 4, -2. So right here, and then I move it 7 units up to get to 4, 5. So right here, and now I would I would stretch this point by 2 because the k value is 2. So 4, 5 would become 8, 5. And now I move it 6 units to the left. So 8 would become 2. So 1, 2, 3, 4, 5, 6 to get to here. And then I'd get 2, 5 right there. So that would be the point. So essentially 4, 2 translated to that point right there. Transformed to that point right there. And likewise, so on and so forth. If we're looking back at domain and range of my transform function right here, notice that point, 0, 0 became that point. So that's why there's no arrowhead there. It's, after I got like a few points, I draw the arrow that way. So I would just say that x has to be larger than or equal to -6. And then it's, element of the real numbers. Y is an element of the real numbers such that it's smaller than or equal to 7, right? Like we could see there. Moving on here, we have another one. For these types of reciprocal functions, folks, what I require you to do, or what's generally the recommended procedure, is to, after we've established what the parent function looks like, it's common practice to draw the asymptotes. So y equals 0, x equals 0. Here, you got to just remember first to factor, right? You got to factor out that 3 to get it to look like this. So this is the proper, in function format right here, it shows the proper horizontal translation. But what I was saying back here with the with the transform function is you want to draw in the asymptote. So here, the asymptote moves, like right here, it's, you know, that line right there, x equals 0, moves to x equals 5. It shifts 5 units to the right, right? So everything shifts 5, so like that. And then the asymptote y equals 0 shifts 4 units down. So there you go, I got y equals -4. So those are the asymptotes. And then I've done a few points here, like 1, 1, 1, half, 2, -1, -1, and some points down here. But in reality, you just need to put 2 points, and then the rest you can kind of, like 1 point in this quadrant, 1 point in this quadrant. So like, for example, like going back to the parent function, 1, 1, and -1, -1 is sufficient enough for me, because once you've done that, you kind of know the gist of the curve, how it looks like. But yeah, you can get that. So that's that. Here we got more on the domain and range. Again, you're looking at, well, in the domain, it's the x, right? So of the parent function, sorry, the transform function. So you're saying that, well, it's element of real numbers such that x cannot be equal to 5. And in the range, it's y is element of real numbers such that y is not equal to -4. That's what the reciprocal function looks like after it's transformed. Again, you got to make sure to factor out here. This 2 right here is being multiplied by, you know, the 1 on the outside. Hence, that's the reason why it's a vertical stretch. It's like my a value. And then I got my 1 over x here with a k value of 3 and a d value of 5. So it's 5 units to the right. And then a c value of, or I would say like the, you know, the vertical translation 4 units down. We'll get more into like talking about the letters in another video when we generalize, but that is how that looks and how that works. Cool. So that brings us to the end of this video. Here is the homework for lesson number 6. It's this worksheet below. So we're looking at transformations of functions, again, horizontally, reflecting and scaling. So try some of these questions out. They're very good. We could try one of them together right now just to get the idea. So if I'm looking at, let's say, I don't know, number 3 here. So this is the function that's given to me. So these points right here. Notice here, this is the transformation that I'm trying to apply. So a k value of a half, right? So this corresponds to a horizontal, and being able to describe this, horizontal stretch, by a factor of 2. So all my x values get multiplied by 2, essentially. So this x value of, you know, that point right there, -4, 3, gets multiplied by 2 to give me -8, 3. This point right here, -2, 3 becomes -4, 3. So this segment right here gets transformed to that segment right there. And then I do this point. Well, 0, 0, 0 multiplied by 2 is just stays 0, so it goes like that. This point right here, 2 gets doubled, the x-coordinate gets doubled, same y to get to that. So I'd connect it like that, right? And then, let's see. Yeah, that looks good. And then this point right here, 4, -2, becomes 8, -2. So it just stretches horizontally like that. And there we go. That's what my function, my parent line, my original function, when it's undergoes this transformation, a k of a half, it gets stretched by a factor of 2. Horizontally, that's what it looks like, right? And you could do the other questions just that way. All right. Thank you, and have a great rest of the day.